To predict what kind of a hybrid orbital a central atom in a molecule may have, we need to determine the total number of bonding pairs and lone pairs. This information we can get from Lewis structure, but actually it will be very useful if we can combine this with the VSEPR theory to count the bonding pairs and the lone pairs, also to understand the molecular geometry. Now let's review a VSEPR theory based on this comprehensive table. So if from a Lewis structure that in your molecule you have two terminal atoms bound with the central atoms, and there's no lone pairs, so therefore the bonding pairs you have two. The bonding pairs here simply refers to have a terminal atom, two terminal atoms. Doesn't necessarily tell us what kind of bond we have. It can be single bond between AX, a double bond between AX, or even triple bond. But in this scenario, we have no lone pairs, so therefore two bonds give us AB2 or AX2 configuration. The molecular geometry is linear. And then when we have total of 3 bonding pairs and lone pairs, and we have two scenarios. First, 3 bonding pairs, no lone pairs. That is the AX3 boron trifluoride. In this case, we have a trigonoplanar configurations, and the bond angle is 120 degrees. And here we and also in the other scenario, we have 2 bonding pairs and 1 lone pairs. So 2 plus 1 equal to 3. The total arrangement of pairs, that's the key thing here. The total arrangement of the pairs is trigonoplanar, including 2 bonding pairs and 1 lone pairs. And here AX2E, that's again 2 bonding pairs, 1 lone pairs. Overall arrangement of pairs, it is still trigonoplanar right here. But when we talk about the molecular geometry, we only focus on the atoms, not including lone pairs. So therefore we have AX. Here we call it the band structure. Okay, right here we call band structure. And again, in trigonoplanar, perfect as symmetrical trigonoplanar, we have 120 degrees at the bond angle. But in here, when we have a lone pair, in the class we know that lone pair has a bigger size compared to the bonding. So therefore, lone pair will push these two bonds closer to each other compared to 120 degrees. So the bond angle in this case, we'll say it's close to, but smaller than 120 degrees. Example is the sulfur dioxide molecules. Okay, and also I want to talk a little more about this. If you draw the Lewis structure of sulfide dioxide, you will find the Lewis structure of sulfur dioxide has sulfur right here, has lone pair, and it forms double bond with each oxide. So the key information here is when we consider the pairs, the bonding pairs, lone pairs, the bonding pairs and lone pairs, we count the bonding we count the bond between the central atoms or terminal atoms as one bonding pair, regardless it's single atoms, it's single bond, double bond, or even triple bond. So here we have a double bond here, double bond here. Each of them is considered as a bonding pair, and this lone pair is considered with one lone pair. So therefore we have 2 bonding pair plus 1 lone pair. Total we have 3 total pairs, and these total 3 pairs determine the arrangement of pairs in this molecule, sulfur dioxide, as trigonoplanar. Okay, and actually this trigonoplanar arrangement is needed to determine the central atom's hybrid orbitals. Okay, let's move on. So when we have 4 total pairs, we can either have 4 bonding pairs, no lone pairs, 3 bonding pairs, 1 lone pairs, 2 bonding pairs, 2 lone pairs. All of this, they have arrangement of pairs as tetrahedral. This arrangement of pairs is not the molecular geometry. Arrangement of pairs, molecular geometry are different. So all of these 3 scenarios, they are all tetrahedral for arrangement of pairs, but they have a different molecular geometry. First, AX4, no lone pairs, is tetrahedral, like methane, and bond angle is 109.5 degrees. And for 3 lone pair with for 3 bonding pairs and 1 lone pairs, it's trigonopyramidal. Because when we consider the molecular geometry, we only consider atoms, that it is trigonopyramidal molecular geometry with 1 lone pair on this side. And because lone pair is taking more space than molecular bond, chemical bond, the bond angle here is close to, but smaller than 109.5 degrees. The example is ammonia. And we have 2 lone pairs and 2 bonding pairs. Although the overall molecule of the arrangement pairs is tetrahedral, the actual molecular geometry is bent here. Alright, AX2E2 has a band structure. The lone pair, the bond angle here is much smaller, a little bit smaller than 109.5 compared to trigonopyramidal case. That is for water. Okay, let's move on to the next 2 cases. If the total pairs is 5, then we have 1, 2, 3, 4 cases that we have 5 bonding pair, no lone pair, 4 bonding pairs, 1 lone pair, 3 bonding pairs, 2 lone pair, 2 bonding pairs, 3 lone pairs. All of this, okay, because they have 5 total pairs, the arrangement of pairs is trigonal bipyramidal. Arrangement of pairs is trigonal bipyramidal. But molecular geometry is very, very different. When there's no lone pairs, it is AX5. We have this geometry. We call it trigonal bipyramidal. And the bond angle we have in this geometry are 90 degree and the 120 degree for those 3. Okay. For the example is phosphorus pentachloride. But when we have 4 bonding pairs, 1 lone pairs, the lone pair is better to be put at the central plane because it's less crowded compared to the terminal bond. So this structure is called seesaw or distorted tetrahedron geometries. And bond angle you can see is about 90 degree and it's less than 120 degrees. The example is sulfur tetrafluoride. If we have 3 bonding pairs and 2 lone pairs, it turned out it's less crowded that we put 2 lone pairs in a plane like this and push these 3 bond towards that directions. The reason for that is if you put a lone, for example, if you look at here, if you put a lone pair here, the bond angle between lone pair is 90. It's too close. But if you put a lone pair here, the bonding degree between this lone pair is about 120. It's much larger than 90. So therefore, this is less crowded. Therefore, it is more stable to arrange lone pair in this way. And this molecular geometry is called T-shaped. The bond angle is about 20. Okay, an example is chloride trifluoride. And the last one in this case 2 bonding pairs, 3 lone pairs. It turned out it's less crowded again to put lone pairs in the plane. Okay, in this case, the degree, the angle between each lone pairs is 120, much larger than 90 degrees. And therefore, AX2E3 geometry, we have XAX on the line. It is linear geometry. Okay, and the bond angle 180. The example is xenon difluoride. Okay, when we have total of six pairs, including bonding pairs and the lone pairs, we have 3 scenarios will be considered here. First, 6 bonding pairs, no lone pairs. And second, 5 bonding pairs, 1 lone pair. And 4 bonding pairs, 2 lone pairs. All of this, the arrangement of pairs. Here again, pairs including bonding pairs and the lone pairs. The arrangement of pairs is octahedral for all of them. But the molecular geometry are different. First, AX2, no lone pairs, 6 bonding pairs. It is octahedral. The bond angle here is 90 for adjacent bond. Example, sulfur hexene fluoride. But when we have 1 lone pair, because each position is equivalent, it doesn't matter where to put it. We put in here, lone pair. The geometry, the molecular geometry, which is called a square pyramidal. And the bond angle here is about 90 degrees. This close to, but it's not exactly 90 degrees. It's slightly smaller than 90 degrees, because lone pair push this bond towards to this bond. So an example is iodide pentan chloride, and we have 4 bonding pairs and 2 lone pairs. Although the arrangement of pairs is octahedral, the molecular geometry here, it turned out we have is less crowded or more stable, that we put lone pair on either side of this plane, because they are further from each other. And this molecular geometry is called square planar. All 5 atoms, AX4, on the same plane, and it's symmetrical. And the bond angle in this molecule is 90 degrees. The example of the molecule is xenon tetrafluoride. Okay, now after knowing all of this, how can we determine the hybridization state of the central atoms, or the hybrid orbital of the central atoms? To determine that, actually, what we need to know is the arrangement of the pairs: octahedral, trigonal bipyramidal, and the first 3 cases, linear, trigonal planar, and tetrahedral. So here let's review it. Okay, so when you have central atoms has arrangement of pairs as linear, again, arrangement of pairs, not molecular geometry, not necessarily the molecular geometry. For example, here beryllium chloride is linear. We have learned that from the VSEPR theory, and therefore the hybrid orbitals central atom of beryllium has is sp. 1s and 1p. Sp form the 2 hybrid orbitals, and it is linear. Another case is carbon dioxide. And from Lewis structure, we know it's carbon from the 2 double bond with 2 terminal atoms, no lone pairs. And in this case, we have 2 bonding pairs. Each bonding pair has 2 bonds. And we have 2 bonding pairs, no lone pair, is linear. And this linear arrangement of pairs tell us carbon, central carbon, must have sp hybridization state, or has 2 sp hybrid orbitals. Okay, then we move on. When the arrangement of the central atoms is trigonal planar, For example, boron trifluoride, the trigonoplanar arrangement of central atoms leading to sp2 hybridization state of the central atoms of boron. And we have 3 hybrid orbitals. So here we do not have the lone pair and the 3 bonding pairs. But what if we have the molecule as sulfur dichloride? The Lewis structure of sulfur dichloride is sulfur has a lone pair here and form a double bond with one oxygen and a double bond with another oxygen. In this case, we have 3 pairs, 2 bonding pairs. Each bonding pair has a double bond, and 2 bonding pairs and 1 lone pair. Overall, we have 3 pairs, and arrangement of 3 pairs is trigonoplanar. But keep in mind, the molecular geometry here is banned because molecular geometry does not include lone pair. But when we have a 2 bonding pair, 1 lone pair, the arrangement of pairs, 3 pairs, is trigonoplanar, and this trigonoplanar arrangement of the 3 pairs leading to sp2 hybridization of the central atoms, which is sulfur here. So if I ask you what's the hybridization state of the central atoms in sulfur dioxide, you need to first get this Lewis structure and then figure out there's a 2 bonding pair, 1 lone pair, 3 of them leading to trigonoplanar of the arrangement of the 3 pairs, including lone pairs, and this arrangement leading to sp2 hybridization state of the sulfur. Alright, once you understand this, you can apply this with all other scenarios. For example, when for the methane ammonium cation, in these 2 cases we have a 4 single bond and no lone pairs, and the arrangement of this 4 bond is tetrahedral, right here, tetrahedral, and is lead to the hybridization state of the central atom, carbon, nitrogen here, sp3. That means we have 4 hybrid orbitals. However, when you have ammonia, NH3, the Lewis structure is nitrogen has lone pair and form the 3 hydrogen. And because we have a 3 bonding pair, each of pair is the single bond, and 1 lone pair. Total we have a 3 plus 1, 4 pairs, and the arrangement of these 4 pairs should be tetrahedral and leads to sp3 hybridization state of the central atoms, which is nitrogen here. So therefore, ammonia, NH3, nitrogen has sp3 hybrid orbitals. 3 of them form the sigma bond with hydrogen, and 1 of the sp3 bond holding the 2 lone pair. How about water? In water, central oxygen has 2 lone pairs, and it also forms a 2 single bond with hydrogen. Alright. Then we have 2 bonding pairs, each is a single bond, and 2 lone pairs. So 2 plus 2, we have 4 pairs. And for 4 pairs, arrangement of that should be tetrahedral. And this leads to sp3 hybridization state of the central atoms oxygen. And 4 sp3 bond form the 2 sigma bond with hydrogen, and also host the remaining 2 sp3 hybrid orbitals holding 2 lone pairs. Okay, again, to determine the hybridization state of the central atoms, we need to pay attention the arrangement of all pairs, including bonding pairs and lone pairs. That will tell us the hybridization state of the central atoms. And then, if we move on, let's look at the remaining two cases. Then you will imagine that for a given molecule, if you have 5 pairs, that means the number of the bond and number of lone pairs, if they equal to 5, the arrangement of pairs will be trigonal bipyramidal, and this will lead to sp3d hybridization state of the central atoms. For example, here phosphorus pentachloride, no lone pairs, or a bond, there are 5 single bond, and the phosphorus will have sp3d hybridization state, and in this case molecular geometry and arrangement of the 5 pairs, actually 5 bonds, are all trigonal bipyramidal. But how about sulfur tetrafluoride? So it turned out the Lewis structure for sulfur tetrafluoride, we have sulfur at the center, 4 bonds with 4 single bonds with 4 fluoride. We'll write here fluoride and fluoride and fluoride and fluoride and 1 lone pair. Okay, so in this case we have 1, 2, 3, 4 single bond as 4 bonding pairs and 1 lone pairs. 4 plus 1 is 5. Therefore, the arrangement of the 5 pairs should be trigonal bipyramidal, and the hybridization state of the central sulfur atom should be sp3d. Although the molecular geometry here is seesaw or distorted tetrahedron. Okay, so one thing I can explain a little bit here is these 2 bonds. All right, so let's make this a little bit more clear. If you will learn organic chemistry in the future, you will see that to represent the spatial geometry of the molecule, these 2 notations will be handy. So first, this normal single bond or bond, a double bond, like this, like draw a simple line, it tells us fluorine, sulfur, fluorine, these 3 atoms are in the same plane. And this lone pair, they are the same plane. This is the plane. And if the bond represent as this dashed line, but from smaller to longer, from smaller to longer, this means this bond is below this plane. This bond is below this plane. On the other hand, the bond shows this solid, like triangle shape bond. That means this bond is above this plane. Now you can imagine a bond below this plane, a bond below this plane, and we have a fluorine, sulfur fluorine, and this lone pair in the same plane. It will be clear for the reader what the actual molecule will look like. But if you don't get that for this course, that's totally fine. Don't worry too much about that. The key thing is sulfur tetrafluoride, because of its lone pair and 4 bonds, the central arrangement, the arrangement of 5 of these 5 pairs leading to trigonal bipyramidal, and the hybridization state of the sulfur is sp3d. There's a 5 sp3d bond. 4 of them form this sigma bond, sigma single bond with fluorine, and the remaining sp3d orbital hosts these lone pairs. And then another case in trigonal bipyramidal arrangement is chlorine trifluoride. So Lewis structure of chlorine trifluoride is chlorine has 2 lone pairs, and it forms a 3 single bond with fluorine. In this case, we have 3 single bonds, 2 lone pairs, 3 plus 2, 5 pairs, leading to we'll have trigonal bipyramidal arrangement of these 5 pairs, and that leads to the central atoms chlorine has sp3d hybrid orbitals. 3 of these 5 sp3d orbital form a single bond with fluorine, and the remaining 2 sp3d orbital host these 2 lone pairs. And another case is xenon difluoride. Xenon difluoride. The Lewis structure of this molecule is xenon has 3 lone pairs and forms a 2 single bond. If you look at the Lewis structure, xenon has 3 lone pairs and 2 single bonds. So therefore 3 lone pair plus 2 bonds, there are 5 pairs, leading to trigonal bipyramidal arrangement of these 5 pairs, and therefore central xenon atom has sp3d hybrid orbitals, and 2 of these sp3d orbitals form a sigma bond with each fluorine, and the remaining 3 sp3d orbitals host the 3 lone pairs, and overall molecular geometry is linear. Okay, that actually conclude all the possibility for the total number of pairs 5. In the last scenario, when we have 6 pairs, the 6th pair will have octahedral arrangement and leads to sp3d2 hybrid orbitals or hybridization state of central atoms. For example, sulfur hexene fluoride. We have this sulfur fluoride, 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 fluoride. Then no lone pairs, we have this octahedral arrangement. You can imagine from our explanation in here, we have the plane, like this plane, fluorine, sulfur, fluorine on this plane, but these 2 bonds are below this plane, and these 2 bonds are above this plane. Okay, how about the case with lone pairs? For example, iodide, pentan fluoride. The Lewis structure of this molecule is iodide has lone pair, 1 lone pair, and 5 single bond with fluorine. And in this case, we have 1 lone pair and 5 bond pairs, total of 6. The 6 pairs have octahedral arrangement and leading to sp3d2. 1, 2, 3, 4, 5, 6 lead to sp3d2. That is a 6. There are 6 hybrid orbitals. Again, 1 s orbital, 3 p orbital plus d orbital, total of 6 atomic orbital leading to 6 hybrid orbitals. And in this case, 5 of these sp3d2 orbitals form the sigma bonds with 5 chlorine, and the remaining sp3d2 orbital hosts this lone pair. The last case I'll show here will be xenon tetrafluoride. So the Lewis structure of xenon tetrafluoride is there are 2 lone pairs on xenon, and the xenon forms the 4 sigma bond with 4 fluorine. So the arrangement of these 4 bond and 2 lone pairs is octahedral, and it should be xenon has lone pairs on top, lone pairs at the bottom, and we have 4 bonds in the central plane. Okay, in this case we have 4 bond pairs and 2 lone pairs. 4 plus 2, 6 pairs. The arrangement of these 6 pairs is octahedral, and therefore the hybridization state of central xenon atom is sp3d2. And the 6 sp3d2 orbitals, 4 of them form a sigma bond with fluorine, and 2 of them host 2 lone pairs. Okay, this actually concludes the complete structure in which shows how we can predict the hybridization state of the central atoms given its Lewis structure. The key thing is counting the total number of pairs, including bonding pairs and lone pairs. Thank you very much.